All right, in this video, we're going to take a look at classifying our discontinuities. All right, but before you can think about or try to classify discontinuities, you really need the definition of continuity at a point. So we're going to go over that first and then show how that's going to lead to our discontinuities. A function f is continuous at c if the following three conditions are met. 1, the f of c is defined, so the value of the function at c is defined. The limit as so at that point C, you're going to look and check to see if the left and the right side limits exist and are equal, and then the overall limit will exist. Third thing, the limit as x approaches C of the function is equal to the function value at C. Okay, so if any of these three conditions is not met, continuity at C fails. All right, so in other words, f of x would be discontinuous at C if we did not have just one of those things true. All right, now let's go ahead and then kind of take a look at classifying the discontinuities. Okay, so really we've got removable discontinuities and non-removable. Removable discontinuities, it's referred to as point discontinuity, and it's known as a hole. We have a hole in the graph. All right, I think of removable as in if I can patch that hole and make the function continuous, then I know it's going to be removable. All right, now for your non-removable, okay, you could have a jump discontinuity. All right, this is a function. We've clearly got a jump right here. All right, if I go back, I didn't do it on the first one. We will here in a minute, though. On this jump discontinuity, coming from the right, I have a y value down here. Coming from the left, I have a y value all the way up there. So the limit from the right and the limit from the left doesn't exist. So the overall limit doesn't exist. So that's breaking rule number 2 of our definition of continuity at a point. Okay, now here, in this particular case, all right, coming from the right and coming from the left, the limit is going to exist. However, with that hole right there in that picture, f of c is not defined. So at that point, the function is not defined because of the hole. All right, the oscillating behavior, that's kind of in a unique category of itself. It is considered to be non-removable. All right, the oscillating behavior, you're just oscillating back and forth so much there at any given point C that you cannot determine a limit. All right, therefore, we've got some discontinuity. It's said to be a removable discontinuity. Now, this last one here, we've got a vertical asymptote. All right, so again, in this particular one, you've got a limit coming from the right that would be negative infinity, a limit coming from the left, which would be positive infinity. So that limit there does not exist. This is also referred to as unbounded behavior because the graph is just going off into infinity forever and ever and ever. But this is an infinite discontinuity. So these are all non-removable, but then you can say, okay, this is non-removable, but it's a jump. This is non-removable because we have an infinite discontinuity. So just to be able to clarify a little bit more specific other than just removable and non-removable. All right, so now that we've got some background, let's take a look at some examples here. I did put this up here in the corner for that definition of continuity just for reference in case we need to look at this. All right, so you can do it randomly. You could go left to right across the graph. There's a lot of different things that we could do here. We can start over here and just be pretty consistent here. So at x equals -7, all right, let's write down x equals -7 because that's my c value. All right, well, what do we got going on here? Okay, so clearly the function is not defined to the left of -7. Okay, so my limit's not going to exist here because coming from the right, it is defined as 2, but coming from the left, the function is not defined. So clearly we've got a discontinuity going on here. We could say it's a hole. All right, so we could say it's a hole. All right, but we could also, it is the end of the graph because the function is defined right there at x equals -7. The function value is 4. So on some websites, I have heard people say, okay, well, it's an endpoint of the graph. The function is defined. Nothing's defined to the left there. Let's look here. We've got a hole right here. It's at x equals -3. So at x equals -3, I have a hole. All right. think of that as, could I fill that in and then the function become continuous? Yes. All right, so this is removable. I guess I could also classify this one up here as removable as well. All right, now our next point of discontinuity is going to be here at 2. So x equals 2. All right, now what's going on? Well, clearly we can see it's a jump. The limit from the right and the limit from the left does not equal. All right, it is classified as a jump, so this would be a jump discontinuity. All right, jump discontinuities are non-removable. And then I've got this vertical asymptote going right here. The limit from the right and the limit from the left does not equal. All right, I've got that unbounded behavior. All right, so that's just kind of to describe it. It's unbounded behavior. All right, it's actually an infinite discontinuity. So we'll write infinite for infinite discontinuity. Infinite discontinuities are non-removable. And then let's also look here at x equals 6. All right, the function value is defined. The limit from the left is defined, but because the function is not defined here to the right, the overall limit doesn't exist there. Best thing there is just, like I said, on some websites, I've heard that defined as, okay, it's an endpoint, so it's going to be not removable because there's nothing there to fill in there. Let's just say it's an endpoint and leave it at that. All right, so the main things are pretty much the things in the center. We've got those infinite discontinuities. All right, we've got jumps and we've got holes. So those are your main 3 areas that you're going to find. All right, different professors, like I said, different websites are going to classify the ends a little bit different. And on this graph, compared to the second example I do here, we've definitely stopped. The graph is not going off into infinity in any direction. Okay, so then that's when you're going to have to deal with those endpoints. All right, let's go ahead and take a look at another example here. All right, now how this graph differs from the other one, this part of the graph goes off to infinity here. This also goes off to infinity there. Okay, so a little bit different than what that last graph looked like. But again, you could just go left to right across the graph. All right, this may not be very easy to see here on this first one. I've got a jump going here. These 2 holes are open. No matter how clear it doesn't look, they are open dots right there. There is a filled in dot up here, so the function is defined, but my limit from the left and my limit from the right don't exist, so the overall limit does not exist. So I've got an x equals 0. All right, so that limit does not exist, so it's a jump. And when it's a jump, then it is a non-removable discontinuity. So I'm going to say jump. And then we're going to say non-removable. All right, keep going. I see a vertical asymptote here at x equals 1/2. All right, so since I see the vertical asymptote, I know it's an infinite discontinuity. Again, the limit doesn't exist. All right, so infinite discontinuity. So we'll put infinite. When it's an infinite discontinuity, it is non-removable. I'm going to abbreviate that time since I'm out of room on my paper. If I keep going here, I've got an x equals 1. All right, again, the function is defined here. It's not defined here. Coming from the right and coming from my left, the limits do not exist. So this is another jump, again, which is non-removable. All right, so keep going. The next place is a vertical asymptote at x equals 3. We've got infinite behavior going on, so unbounded behavior. This is going to negative infinity. This is going to positive infinity. The left and right side of those limits do not exist. Okay, so this is going to be an infinite discontinuity. And again, that's non-removable. And then coming over, last one here, looks like a hole in the graph at x equals 4. All right, so we are going to classify it as a hole. All right, and then again, think of that. If it's a hole, I should be able to fill it in and make the graph continuous at that part right there. And I could do that. Okay, so then that means it is removable. All right, so just a quick couple of examples there with some definitions. You really have to understand the definition of continuity at a point to be able to then classify your discontinuities. There is a connection there. Okay, definitely. Thanks for watching. If the videos are helping, don't forget to share with your friends so that they can benefit too. And don't forget to subscribe to the channel. Thanks.